All right, guys, let's go ahead and get started. I'm going to start off today with some slides. So we've already gone over this with our in our tutorials, but I thought I'd just give you a little bit of background and kind of clean stuff up a little bit. So yeah, what is the purpose? Why bother predicting volatility in the first place? So there are several applications within finance. A big one is option pricing. Usually future volatility is an important input in any pricing framework. Also in modern portfolio theory, the volatility of constituent asset prices within the portfolio, of assets within the portfolio, is a measure of portfolio risk. So it comes up there. It's also worth noting that forecasting volatility is a lot easier than forecasting prices or expected returns. So it makes for a good classroom example. And that's part of why we're doing it. Let's talk a little bit about realized versus implied volatility, because this can be a point of confusion for people. Realized volatility is also sometimes referred to as historical volatility. And what that means is it's the standard deviation of returns that have already occurred, which is why it's called historical volatility. So you've got a series of returns that have happened. You take their standard deviation, and that is realized volatility. It gets a little bit confusing because we can talk about future realized volatility, which means realized volatility that will occur over some period of time in the future. So there is that use of the term. And then there's implied volatility, which is a prediction of future volatility that you can infer from option prices, typically by inverting the Black-Scholes formula. So our objective is going to be to forecast future realized volatility, which hasn't occurred yet, from past realized volatility, which has already occurred. So that's what we're doing. So the definition of realized volatility is probably familiar to most of you. So let's say we've got close prices of some asset. Then we just want to take the average. We want to take their log returns, square them all, take their average, and that's actually the variance. And then so to get this, the volatility, you would take the square root of that, which is the standard deviation. And typically you annualize, you speak of volatilities in annualized terms. And so you need to multiply this by the square root of 252. And you could also replace this, this calculation with just regular returns instead of log returns. And depending on your audience, that might actually be preferable. It's not going to change your values very much. And Chris Bemis actually says something funny that I think captures it, and that is, why not do your analysis with the returns that you're actually going to be measured on? And I think that's a succinct way of putting it, but lots of different ways to think about it. But ultimately, using regular returns versus log returns isn't going to matter that much. This should actually say efficiency and bias. I think I've been in the machine learning literature too much. So when we have some estimator of future volatility, we could measure its efficacy in a couple of different ways. One is its efficiency, and one is bias. So, and here's how they're defined. So in terms of efficiency, you're basically trying to get a sense for how volatile your estimates are. And what you do is you take the variance of the close to close realized volatility and divide that by the variance of the estimator volatility. So this is, variance of the close of realized volatility, variance of the estimator. I don't know why they do it this way. To me, it feels more natural to have it be the reciprocal. I think they do it because they want bigger numbers to be better, right? Because the smaller this is relative to this, that's good. And that's going to make this quotient bigger. And then there's also the bias, which is basically, on average, how much error is there between the realized and the estimates. So, and one thing I realized is that I didn't actually do these in the tutorials. So I went and actually recalculated them within the tutorials, and we'll take a look at that. It's interesting. The GARCH seemed pretty off in terms of bias. They all seemed pretty reasonable in terms of efficiency. And what was I going to say? And all pretty similar in terms of efficiency. So we can classify various methods of estimating. So there's the sampling methods. And these assume that stock prices are a diffusion process, some kind of continuous process, and we're seeking to estimate the volatility via discrete sampling. So the classic estimator under this is the close-to-close estimate, which is basically calculating historical volatility over a previous period of time and just projecting that to be future volatility. But there were some more advanced estimators that were developed in the 80s and 90s, and those take into account open, high, low, and close prices. The first one was the Parkinson, and then others followed, the Garmin-Kloss, the Roger-Satchel, and the Yang-Zhang. And we've gone through all of those in the previous tutorials. So, and we're going to consider versions of these that assume zero drift, so that there's zero mean return. Some final remarks. So it's typical when you're doing a sampling method to use a historical window that's the same tenor of the volatility that you're trying to estimate. So if you're trying to estimate weekly volatility, you use 1 week of historical data. If you're trying to estimate monthly volatility, you'll use 1 month of historical data. Sampling methods inherently don't account for clustering and the mean reverting nature of volatility. So GARCH is an example of a model that directly accounts for some of these. And I'm not going to recount the estimators, the definitions of these estimators. It's kind of some gruesome formulas that I didn't want to put into LaTeX. And so I'll just refer to the papers and also the Python tutorials where we've actually implemented it in code. Okay, so let's talk a little bit about inference methods, the most important of which is GARCH. So, and I borrowed a lot of this presentation and notation from Hull's treatment of the topic. So let's say that the UIs are log returns of some asset. Then the maximum likelihood estimate of the end day variance is this formula. You take the difference between a given observation and the mean, you square it, you take their average, the standard variance estimate. The reason why I did maximum likelihood instead of unbiased is because maximum likelihood has this just M, whereas unbiased would have M-1, and I always find that a little bit annoying. So, and this is the standard way that people do it in practice anyway. Typically, you're dealing with large enough amounts of data where the difference between M and M-1 doesn't really matter. And U is the mean log return. So we're again going to assume that there's zero drift. And that way we can just simplify this down to the mean of the UI squared. If you look at this estimator, we're giving all of the log returns, the historical log returns, equal weight. And it may make more sense to give closer terms more weight, more recent terms, more recent log returns, more weight. And so we could apply some kind of weighting scheme where we now have these alphas that that aren't just 1 over M, but rather decrease through time and all sum to 1. So you could apply a variety of weighting schemes. And we could extend this weighting scheme model even further by assuming that there's some average long run variance. And so the model would take this form where you've got now your weighting scheme, but you've also got gamma times some long-term volatility. and you'll want to make sure that the gamma plus all the alphas sum to 1. And this is what's called the ARCH M model, where you're taking, and the M comes from the number of historical returns you're taking. And it's one of the simplest variance estimators that accounts for both volatility clustering and also mean reversion. There is some long-term average that gets more weight, and more recent observations get more weight as well. So let's talk about exponentially weighted moving average. So again, we've got our estimator with some weighting scheme of alphas. And we're going to assume that the weights decrease exponentially, so that each subsequent one is just the previous one multiplied by some lambda between 0 and 1. That's called the exponentially weighted moving average estimator. And you can show with a little bit of arithmetic that it reduces down to this convex combination of the previous variance. Oh, there's again an error here. I'm sorry. This should be the squared return. So yeah, I need to go back and clean up these slides. I will do that so there's not confusion moving forward. But anyway, what this should say is that the end day estimate only depends on the n-1 day estimate, and then the n-1 day return. So the GARCH 1-1 model takes the following form. So we've got that our estimate is equal to gamma times some long-term volatility plus alpha times the squared return from the previous day plus beta times the variance estimate from the previous day. So, and we need all these coefficients to sum to 1. And the exponential weighted moving average is a special case where gamma is equal to 0, alpha is equal to 1 minus lambda, and beta is equal to lambda. And typically we'll rewrite this as just omega here. And then, you can back out what gamma and, oh geez, this should say gamma. My apologies. And typically, this is to actually come up with estimates for these coefficients. It's an optimization problem that utilizes maximum likelihood methods, and you typically use 5 to 10 years worth of data to fit the model to this. And if you have the model parameters fit so that you have a 1-day volatility estimate of this, you can actually extend that to an n plus to a forecast for multiple days in the future using this expression. And don't get too bogged down in this. I'm not too worried about it, but you will see in the GARCH, what the GARCH produces is a bunch of single day forecasts in the future. So 1-day variance estimates, and then you'll put 5 of them together to get a weekly estimate. And let's jump over to the tutorials, and I'll kind of show you. Just run all these quickly. I think they're already run anyway. So for the close-to-close estimator, right, I had a bias of about 1%, and the I think that's pretty decent because I think the average realized volatility was something like 13%. Let's double check. 13.7%. So that seems not huge relative to the overall size. And then an efficiency of 0.89. So the close-to-close estimator had slightly more variance than the actual realized volatility. Parkinson was a little bit better on both fronts, less bias, about 50 basis points, and had an efficiency of greater than 1. So that's good. Garmin Kloss, pretty similar, even less bias. Roger Satchel, similar. These all were pretty similar. So, except for the Yang Zhang. Which was kind of the worst performer in terms of bias. And then let's also look at the GARCH. The GARCH was actually really bad, which was kind of surprising to me in terms of bias, especially because it's the fanciest of all of them. Let's see here. Right. The GARCH had a bias of, so I don't know if I did this right. I didn't have time to really check my work, but it seems pretty spot on. And I tried to check in SEP if he said anything about GARCH tending to overestimate volatility, because that's what this is showing. But yeah, it is what it is, I suppose. Without doing further analysis, it's hard to know. Okay, are there any questions on any of that? In that case, let's proceed to talk about option volume prediction. We already went through this tutorial, but I thought I'd just do it again because it's been a couple of weeks just to refresh it. All right, so the function of an option market maker is to provide liquidity to various market participants on options exchanges. So what that means is for lots of different options, typically hundreds of thousands of different options. There's about 1 million options that are listed on the exchange on a daily basis these days. And typically market makers cover, 70, 80, 90% of that. There are requirements that the exchanges imposes in order to get market maker status, which gives them certain privileges. They need to be covering most options. So for any given option at any given time, an option market maker is willing to buy for a price that's slightly lower than what they consider to be fair value, and at the same time, simultaneously, be willing to sell that same option for a slightly higher price than what they think that same fair value is. And of course, determining what is fair value is a big question mark for market makers, but that's their essential business model. And if they're doing their job right, then the more often they trade, the more money they make. So they want to execute as much volume as possible. And these are all computerized automated strategies, obviously, and there's limited bandwidth for all these computers. And so it makes sense for them to direct whatever resources they have towards the underlyings which have the most volume, or to direct their highest speed computing power to the underlyings which have the most volume and are the most profitable. So for this reason, market makers would find it useful to be able to predict option volume rankings for different underlyings. So that's what we're going to try to do here. And this is based a little bit on some work that I start. The essential problem is one that we tried to address, or we're starting to address, when I worked at an option market maker in Chicago. And so here's what we're going to do. We're going to choose a universe of moderately liquid underlyings using 2016 volume data. And the reason we're going to go with moderately liquid is because if you just look at the top 10 or top 20 overall most liquid underlyings, it's always going to be the same one. It's going to be SPY, IWM, probably some big stocks like Apple and Tesla and Google. And so it actually is, it's a more interesting problem to say, of the 300th to 500th most liquid options, liquid underlyings, can I come up with any kind of predictive model for the rankings of those? Because there's just more variance and volatility between rankings on any given day for given underlyings. So we're going to use 2016 volume data to choose our universe. Then we're going to fit a model for these underlyings using 2017 data. So that's going to be our training period. And then we're going to use this fitted model to make predictions for 1 month in January, which I'll call the backtest period. So this is related to Brady's question of, here's a situation where now we have a true training period and then a true test period in the way that you would have in a finance type of context. Typically, you're training a model with some historical data and trying to make some predictions for the future or the near future. And so the way that you would construct a backtest is saying, okay, so I'm going to train my model for a certain period of time, and then I'm going to use that to make predictions, and then you would roll that forward. So if we were doing this full blown, then we would say maybe our model is to use 1 year of historical data, and we're just going to see what happens if we use 1 day of historical data, predict 1 day, and then roll that 1 year forward for our training period, refit the model, make the next day predictions. That would be probably more how you would do it in practice. I wanted to simplify things and just say, okay, let's fit the model once with 1 year of data, and then we'll make predictions for an entire month based on that one trained model. But it does give you a sense for splitting it up into a training period and then an actual prediction period. I'm also going to define this top N metric, which we're going to use to evaluate the various prediction models. And we're going to use that in future tutorials. I don't know what I'm going to do for an assignment. I'm pretty heavily leaning towards having the volatility because basically I believe your student loan prediction was due today, and then you're going to have 2 weeks to do the volatility forecasting. And it'd be nice to be able to do some other things, but I don't want to make this drag on for any longer than the rest of the semester. And so, so yeah, I don't know if there's going to be an assignment. What I might do for those of you who are feeling very ambitious or want to kind of mess with this data in practice with this data, I can just put up what an assignment would be, and you can mess with it if you want to. And I'm not going to do any typing for these tutorials just because they get a little long. The code chunks get a little bit long. And so we're just going to work through this. Okay, so we just imported the package that we need. Pretty straightforward, NumPy, pandas, sklearn. We're going to grab the data that we need. They're actually pretty decently sized data files. But they shouldn't be taking that long to load though. Well, maybe. So DF stats consists of various implied volatility, total volume, and total open interest for various underlyings for various days. And DF stock is open, high, low, close prices for the underlyings. Again, to select the universe, we're going to use 2016 data. And the universe that we ultimately want to arrive at is the 200 most liquid underlyings that are sort of ranked 300 to 500, and for which there's data for all of 2017. Another thing I wanted to do in this tutorial, and I sort of do it in a lot of tutorials, is give you a sense for all the data wrangling that was involved. So when I did this initially, I didn't think that there was going to be that much missing data, and it turned out there were quite a few underlyings that had missing prices or missing stats in here, and so it took a little massaging and wrangling to find a couple hundred of these that had their own had all the data, and I wanted to kind of show you guys that. So the first thing we're going to do is isolate data from 2016. And now we're going to calculate volume rankings over the entire year for these underlyings. And that's what we're going to use to grab the 300th to 500th most. But first we're going to create a raw universe, which is actually going to consist of the 300th to 700th most liquid underlyings, because we're going to find that some of these have missing data, and then we're going to drill down to the ones that have all the data and then grab the 300th to 700th most within that set. So this is just our raw universe, 301 to 700. And the next thing we're going to do is we're going to grab the data, the stats data for our testing period, our training period through the end of our testing period. And now this code chunk selects the universe. I'll give you guys a couple minutes to just peruse that, and then I'll talk to you about it. What we're doing here is starting with that raw universe of 400 underlyings. We're joining on the stats analysis, the stats and the stock data. And then the important thing that we're doing here is I just visually was able to inspect that there were 272 trading days in this entire period. And so I just hard coded this in. And then re-ranked everything, and then grabbed the 300 most liquid underlyings. So I think this should actually say 300 to 600. Anyway, it doesn't really affect the analysis. So now we have our universe. This is our universe of underlyings. Another little bit of wrangling that we have to do is I again proceeded down the analysis thinking that there were no zero implied vols, and I got some kind of error when I was trying to divide by implied vols. I was getting some infinity values, and so then I had to come back and say, well, okay, there's zero implied vols. What am I going to do with that? And I decided to take care of that in a pretty heavy-handed way, which is just to say I'm going to set those to the average implied vol over all the implied vols that are in this data set. What is that value anyway? $40. Seems like a reasonable number. And of course, there are more sophisticated ways you could do that. You could do a group by and take the mean of the non-zero values within each underlying. That would be probably more accurate, but it was a small number. Not that small, but it's just not going to affect the analysis that much. So I decided to keep it simple. So the next thing I wanted to do was construct the features that I might want to use. I don't use all of them in this in these tutorials, but in case you guys wanted to mess around with them, I just wanted to add some different ones, and I wasn't sure what all I was going to use. So I'll give you a second to take a look at those, and then I'll kind of talk about them. So what do I have here? I have the previous day's implied volatility, the previous day's change in implied volatility, the change in implied volatility from 2 days ago. This is just the volume ranking from that day, which is ultimately going to be the label that we're trying to predict. I've got the daily return, the scaled return, the scaled, and these wouldn't be used as features, but these would be lagging it by 1 day and 2 days. And then the actual rank from 1 day previously and 2 days previously, and the rank change from 1 day previously and 2 days previously. So those are all the features that I thought might be useful. I only analyzed a few of them. And these are for the training period, and we need to construct them for the testing period as well. And the only real difference is that we are filtering by different dates. And then I just wanted to save this data to CSVs to use later. Okay, before we get into any kind of modeling or predictive analytics, let's just do a little bit of exploratory data analysis. So the first thing that we see is that there's a fairly decent correlation between the current day ranking and the previous day ranking. And that makes intuitive sense. If there are just inherently higher volume options, and higher volume underlyings. And so that's going to sort of persist through time. If we did this for the 100 most liquid underlyings, I bet this correlation would be closer to 80%, 90%. It'd be very high for those super high ranking underlyings. They just don't change very much. Another thing we can see is that there's a fair amount of reversion, mean reversion, you could call it, which means that if the rank increased yesterday, it's likely to decrease today and vice versa. And that makes sense too. You know, if for some reason there was some kind of anomalous or idiosyncratic jump up in volume because of something that was going on in that underlying, that's probably not going to persist, and it's going to come back down later. So we can see that in the scatter plot. We can also see that if we calculate the correlation matrix. And the correlation is stronger for the ranks than it is for rank change. So we're going to actually do our predictive modeling on rank. And the backstory behind that is I hypothesized that maybe rank change was actually going to be more useful, a more useful thing to model. And I actually proceeded with the analysis in both ways, and just found that actually predicting ranks just led to higher top end ratios, which we'll discuss next. So the idea here is that we don't ultimately care if we get the volume ranking predictions exactly right. So for example, if we were to correctly guess what the top 10 underlyings were, we don't care if we get the ordering right. And So for that reason, I decided to consider this top N ratio metric, which basically compares the ratio of our predicted top N ranked volume to the actual top N ranked volume. So if I predict a certain 10 underlyings to be the top ranked ones, I calculate what their total volume is and compare that to the actual top N total volume. And this value is always going to be less than or equal to 1. This function right here over the test period just calculates what the top N volume rankings were. And I think I used top 25 in all my calculations, but you could do whatever you want. You can say top 50, top 40. That's a little bit different. So just a way to read this is on January 5th, the top 25, the actual top 25 most liquid underlyings traded about 660,000 options. On the 31st, it was just under 500,000 for the top 25. As you guys have probably noticed as a pattern, I like to come up with simple rule-based predictors as a benchmark for our predictive analytics. And most of the time, I can't beat the simple rule-based predictor all that much. So we've already seen that there's a high degree of correlation between yesterday's volume rank and today's volume rank. And so we could have just a very simple predictor that says tomorrow's volume rank is going to equal today's volume rank. And that's going to be our baseline for comparing our predictive analytics to. So we're going to calculate, average top 25 ratios for the simple rule-based predictor and compare that to the top 25 ratios for our other estimates based on machine learning. So here are a couple of user-defined functions. This one calculates the top N ratio for a given N for a given trade date during the testing period for a given model. And this one actually basically loops through the entire testing period and calculates this top N ratio for each of the dates. I'll give you guys just a couple minutes to peruse this code a little bit to get a sense for what's going on. Let's now see how our simple rule-based scheme did. So here are all the top 25 ratios for the various dates. 76% here, kind of a low of 41 here. And here we see that the average is about 59%. We were able to capture that much volume on average. And then I wanted to do like standard deviation, min and max to get a sense for just how dispersed the outcomes are. And now our first bit of machine learning here is we're going to just do a simple linear regression with a rank 1 lag and a rank 2 lag and see if this model does any better. So this is just fitting the model, and then we feed the model into the backtest function and see what we get. And here we're doing slightly better, right? We're capturing on average about 63%, so we do about 3% better. Standard deviation is slightly smaller, and both the minimum and the maximum are, let's see, are they on the same day as 117? 118, okay. So the minimums are on different days. The maximums are both on that first day. Okay, then let's move on to the next tutorial. So this tutorial is a continuation of the analysis that we did in the last tutorial. And so here's what we're going to do in particular. We're going to now fit a linear regression to 4 different features, see what the outcome, no, I don't think we're actually going to look at the outcome. The next thing we're going to do is we're going to fit a lasso regression to our features to find the ones that have predictive power. And I'll have some slides next time about lasso regression. You can read about it more in Introduction to Statistical Learning. It's pretty intuitive, simple concept. And then we're going to do a little bit of hyperparameter tuning. We're going to do a KNearest neighbors regressor, and we're going to find the optimal number of neighbors. And then we're going to run our back test with this, the KNearest neighbors regression, and use that optimal n neighbors that we came up with. Then we're going to then we're going to do a random forest regressor and find the optimal max depth for that regressor. And then we're going to run a back test using that max depth. So let's import the packages that we're going to need. We are going to read in both our training data and our testing data, which we wrangled previously. And we're going to start with 4 features. We're going to do IV change from the previous day, scaled return from the previous day, and we scale the return by the implied volatility. I don't know if I talked about that before, but if you have a more volatile asset than, like if you have a 50 vol underlying and a 25 vol underlying, then a 2% return on each of those is should be treated differently, right? A 2% return is more likely for a 50 vol underlying than a 20 vol underlying. And so if you scale by the implied volatility, you get more of a sense for how many units of the implied volatility did the underlying move. And then we're going to use the lag from the previous day, and also the rank from the previous day, and also the rank change from the previous day. Let's go ahead and fit a linear regression model. And again, I just spit out the R squared just because I wanted to have some kind of output to show that it ran. Let's check our parameters and see if they make sense. So the coefficient on IV change 1 lag is positive. So that to me makes sense because a positive change in implied volatility could be caused by supply demand effects of increased buying. So option buying increased, that increased implied volatility. And typically that's all sort of related. Something happened in the underlying, or someone has information about something going on in the underlying, and that causes buying to increase, which then causes implied vols to increase. So, and that dynamic could carry through to the following day. So I would expect this to be positive. If you have a jump implied volatility yesterday, then you should have an increase in your volume rank. Scaled return, that one also, basically this says when a stock goes down, when when the price of a stock goes down, you're going to see an increase in the volume rank. And that makes a lot of sense to me, because when a stock goes down, then long positions might get fearful and buy puts, or might get greedy and buy calls. But typically there's more activity that happens, especially with index options. With single names, this is probably less pronounced, but I think essentially true, because the market is inherently long equities. So these long positions are going to get fearful, and there's going to be just increased option buying, both puts and calls, perhaps. So that directionally makes sense to me. The rank 1 lag, again, directionally makes sense. If it has high rank one day, it's likely going to have high rank the following day. And the rank change 1 lag should be negative, as we saw in the correlations, and the intuition also makes sense. If an underlying has a jump in volume one day, it's usually going to revert back at least somewhat to previous levels the following day. Let's talk a little bit about lasso regression. So lasso regression is a linear regression technique which minimizes an objective function that involves residual sum of squares. So standard linear regression is about minimizing residual sum of squares. And so lasso regression takes that into account, but it also takes into account the magnitude of the regression coefficients. And basically it penalizes the objective function by the size of the regression coefficients. And so this can be useful if you have, let's say, a couple of highly correlated features. So unless they're perfectly correlated, the linear algebra is going to work and you're still going to be able to invert the matrix like you need to. However, you're going to have a situation where you have, you know, wildly positive regression coefficients for one of those variables, for one of those features, and wildly negative coefficients for the other features. And so this is something that lasso regression can help kind of cure, because what it does is it has the effect of making the coefficients of non-predictive features equal to 0. And so lasso regression can be a useful technique to do feature selection. And that's how we're going to use it in this setting. There is a lasso regression in sklearn. And so there's this alpha parameter here, which actually controls the level of penalty that is going to be given to the sizes of the coefficients. So let's go ahead and run that now. And let's take a look at our coefficients again. And as you can see, the IV change one lag, it was pretty close to 0 anyway. So the effect size was pretty darn small. And I bet if you did hypothesis testing on it, you would see that this was just not statistically significant. And so the other values stayed pretty much dead on, pretty similar. The scaled return one lag changed a little bit, but all the directions are the same and the magnitudes are pretty similar. So one thing that you'll want to do when you're using lasso regressions is to do cross-validation to determine what the best alpha value is. I just threw in 0.10. So that's what this is basically this chunk of code does this. I'm going from 0.1 to 1 in 10 steps, and I'm going to check the R² for various lasso regressions with a tenfold cross-validation. And as you can see, it really doesn't matter. It doesn't seem to affect the R² at all. Typically, you would go with the alpha value that has the highest R² here, but it doesn't seem to really be affecting things very much. I would be interested in repeating this for all of the features and just kind of seeing how it pans out for multiple features. And that probably would be part of the assignment, the optional assignment that I'm going to give you guys. So let's go ahead and remove IV change one lag, because our lasso regression showed that it has low predictive power. The next thing that we're going to do is just bring in the various functions that we created in the last tutorial for the top 10 ratios. So that's what all these next code chunks do. So this one calculates the top n volume during the backtest period. This calculates the top n ratio. So this is the actual top n volume. These are the top n ratios for predicted versus actual. And then here's the actual backtest code. All right. We're going to fit a KNearest neighbors regression to our data. And the first thing that we'll want to do is do some hyperparameter selection. So the only real hyperparameter of note is the number of neighbors. So first, we're going to do a tenfold cross-validation using R squared as our metric to determine what the optimal value of n neighbors is. So that's what this chunk of code does. Okay, that has finished running. And as we can see, it doesn't really seem to make that much of a difference what value of n neighbors we use. So I decided to use 400 because technically that is the highest R squared, but I don't think it would really matter that much. And so the next thing we're going to do is actually fit the KNearest regressor to the entirety of the training data using n neighbors equals 400. Okay, so that's fit. Okay, and then what I just did was ran our back test for top 25 ratio. And again, we're only doing marginally better than our rule-based predictor. Even with all that fancy work that we did. Okay, so the next thing we're going to do is a random forest regressor. Oh, and let me mention that, you know, in your previous exercise, we did classification with, so far we've done classification with KNearest neighbors and random forests, but if you recall, you can just as easily do regression with those. So that's what we're doing here. And I already ran a cross-validation analysis to determine that n estimators equals to 10 has a good trade-off between performance and runtime. And that cross-validation took a long time to run just because as you increase the number of estimators, it just takes longer and longer. As you guys are probably well aware from your assignment, things can have long run times. So now let's do a tenfold cross-validation to find the optimal value of maximum depth for each of the regressors. All right, so now that has finished running. And again, for max depths kind of in this range doesn't seem to make that big a difference. As you get higher and higher, I think there's probably some overfitting going on and probably some underfitting going on here. So it looks like the highest value that it attains is at max depth equal to 7. So let's go ahead and use that to train our model. So that is trained. And now let's run our back test and cross our fingers. And alas, still not doing that much better. I think it is the best of the 3, but still only about 3 or 4% better. Higher standard deviation too, and min and the max are getting better. It is interesting to note that the first date is the highest, so maybe there would have been, I honestly think that that's just a fluke, but I wonder if there would be better performance if we actually retrain the model every day on the past 1 year of data. But I don't think that's actually the case. I think there'd probably be slightly better performance if we did that, but ultimately, I just think it's just not very predictive beyond the simple rule of yesterday's rank is highly predictive of today's rank, or fairly predictive. So yeah, I will say that in a lot of these predictive modeling things that we do, we just find that what we're doing doesn't seem to be all that predictive. But I think that that's sort of par for the course, especially when you're using real world data. It's hard to find super predictive models. All right, guys, let's get back to it. Now, are there any questions about anything that we went over with the option volume prediction problem? Okay, in that case, let's start talking about some more unsupervised learning stuff. We've already talked about unsupervised learning when we did our PCA analysis work. which I think also, the homework, I believe it was the homework for that one that I posted with the solution. So everyone seemed to have done a very good job and gotten full credit for that. So I hope you at least changed variable names. But we've already talked about unsupervised learning in the context of principal components analysis. And we're going to review some of that today and go a little bit more through the theory. But we're also going to talk about k-means clustering, which is another unsupervised learning technique. In a supervised machine learning problem, what we're trying to do is predict a label from a set of features. And it's somewhat straightforward to judge the quality of our prediction by how closely or accurately our predictions are to the actual outcomes. Unsupervised learning is a little bit different in that there's no labels to predict. What we're trying to do instead is to find interesting structures or data or interesting aspects of the features themselves. So what does that even mean? What is interesting? What is useful? It's hard to really say, and that's what makes unsupervised learning much more subjective and, in a sense, much more difficult. And so today we're going to talk a little bit more about principal components analysis, and we're also going to talk about k-means clustering, and we're going to work through some tutorials. Okay, so here's the context. Suppose we're starting with n observations of p features. And so these are the actual features. So this should say p, not n. Yet another typo. So this is the ith feature observation. And we're going to assume that our feature observations have a zero mean, a standard deviation of 1, i.e. they've been scaled, and that we have more observations than features. What we're trying to do in PCA is to find a low dimensional representation of the data that contains as much of the variability as possible. And we'll talk about what specifically that means. But in general, a set of feature observations lives in p-dimensional Euclidean space, right? Their vectors, they're p unit vectors, or p-dimensional vectors. But as often is the case, usually these feature observations live in a lower dimensional subspace for the most part. And it's the dimensions of these subspaces that are interesting in that the data has a significant amount of variability along these dimensions. And again, we'll talk about specifically what that means. So what does it mean to calculate the first principal component? So what it is, it's a linear combination of the p features. So phi 1, 1 through phi p1, where these, I don't know if it's phi or phi, I'm just going to say phi, where these phi's make a unit vector, which is what this says. You square them all up, you add them together, and they equal 1. And what we require of these phi's is that they are such that the linear combinations of the feature observations, zi1, that look like this, have the largest variation. So if you take the standard deviation of these z's, then these are the coefficients that will give you that largest standard deviation. So this vector of we'll call it phi 1 of these coefficients, and that's called the first principal loading vector. And the elements of this vector are called loadings. So when we, in scikit-learn, when we look at the components underscore attribute of a fit PCA model, we're looking at the loading vectors, the principal loading vectors. And the zi's, those are called the scores of the first component. So if you take linear combinations of all the feature observations and create your zi's, all those zi's collectively are called the scores. So we're seeking to maximize variance, so we'd like to solve the following optimization problem. You want to find the phi's such that the variance is maximized. And if we wanted to rewrite these in terms of the feature observations, the little x's, you could rewrite it like this. And both of these optimizations are subject to the constraint that these phi's form a unit vector, which is all this says. So here's the geometric intuition. So the loading vector, phi1, is the direction in p space along which the data varies the most. So when you project the n feature observations onto the direction of the loading vector, we get the scores z11 to zn1. And so notice here that all we're doing is taking dot products of the feature observations with the phi ones, phi 1i's or phi I1s. And dot products are closely related to vector projections. So this is the vector, which is a direction in p space. And if you project all of our feature observations onto that, what you're going to get, the distance from the origin for each of those projections is simply going to be the scores. And you don't have to worry about that too much. I think this is intuitively clear that this is sort of the direction along which the data varies the most. And one thing to keep in mind is whenever you see dot products, you can typically make some kind of statement about projections. So how do we calculate the second principal component now? So the second principal component is the linear combination of our features that has a maximal variance of all linear combinations that are uncorrelated with Z1. So again, we have the scores, which are just the linear combinations where the coefficients are the components of the elements of the loading vector, the second principal loading vector. And when we say that Z1 and Z2 are uncorrelated, what we mean is that that's equivalent to the first and second loading vectors being orthogonal. So if we go back to this geometric intuition, the first principal loading vector is the direction in p space along which the data varies the most. The second principal component vector is the vector that's perpendicular or orthogonal to the first loading vector, along which the data varies the most. So a lot of times people will talk about doing the following visualization, is that you take the scores from each of the principal components and plot them against one another. And what this amounts to is projecting the data down to the subspace that's spanned by, in this case, the first two loading vectors, and then plotting those projected points. I've done this in a couple of different situations, and I also did this for a tutorial that we're going to go through, and I just find it to be hard to, in the situations that I did it, it was sort of hard to interpret what I was seeing. It didn't seem like there was very much. You'll see the standard iris data set, and they project onto the different principal components, and you can kind of see separations here and there. But in the data that we're going to look at today, I found it hard to see anything in particular. So here's another geometric interpretation. So the first principal component is the line that is closest to the end feature observations. So that's very similar to fitting a regression line to the data. And the first two principal components span the plane that is closest to all of the data. And the first M components span the M-dimensional hyperplane that is closest to all the data. So you can think of it sort of as this higher dimensional regression type of construction. And we can also think of this in terms of approximation. If we take this this geometric interpretation. We can give it this approximation interpretation. So what it says is the M principal component score vectors combined with the M principal loading vectors form a good approximation of the original feature data when M is sufficiently large. So if you take the scores, if you take the linear combinations of the scores, you get back approximately the feature observations. Assuming that the M components that you have capture a lot of the variance, the explained variance, which is what we're going to talk about next. So if you recall from previous tutorials and probably what you've seen before, you can assign a certain percentage of variance explained to each one of the components. And this is going to talk about what exactly that means. So the total variance of our data set is simply the variances of each of the features individually, and then you sum them up. That's what's called the total variance of the data set. And then the variance explained by the mth principal component is the variance of the scores associated with that component. And if you wanted to rewrite that in terms of the feature observations, you could do that like this. And so then the percentage of variance explained for the mth principal component is simply this divided by this. So the variance of a single component divided by the total variance. Let's move on to k-means clustering. So clustering is a broad set of unsupervised techniques in which we're trying to partition the feature observations in such that the partition elements are as homogeneous as possible. So we need some concept of what is sameness or what is homogeneity for these partition elements. And the standard choice is to take the sum of squared Euclidean distances of all the pairs of points in a partition element and then divide it by the number of observations. So basically the average squared Euclidean distance. And in k-means clustering, this is how we basically proceed. So what you have to do is you have to specify the number of partition elements at the outset. So there's a big question mark. So where does that number come from? And probably it comes from some level of intuition about the problem at hand. And that's kind of what I used in the example that we're going to go through in the tutorial. So, and here's how the k-means algorithm proceeds. So you're going to randomly assign each feature observation to a group, just at random, to one of your n groups that you've predetermined. And then you're going to just repeat the following until reassignments don't change. So for each cluster, you're going to calculate the mean vector. You're just going to take the mean of all the components and that's create a vector out of it. It's called the mean vector, and it's referred to as the centroid. And then you're going to reassign each observation to the group whose centroid is closest. And then you're just going to keep repeating that process until group assignments don't change. And this process is guaranteed to converge. However, it's going to converge to a local solution. And because of that, it's important to run it multiple times and then choose the one that leads to the most homogeneity among the groups. And scikit-learn is nice because it takes care of all that for us, and it does run k-means clustering multiple times. Okay, then let's move on to the tutorials. Okay, so k-means clustering, as we've talked about, it's an unsupervised learning technique where we're grouping collections of features into a pre-specified number of groups. And what we're going to be doing in this tutorial is performing k-means clustering on some backtest data of a volatility trading strategy applied to various ETF underlyings. This was based on some work I did for a consulting client a while back. They gave me their permission to just share this data. I won't go into too much detail about what the trading strategy is in and of itself, but it is backtest data from a volatility trading strategy. And the way the strategy worked was it was the same basic trades that were applied to various ETFs, and we kind of examined how the trading strategy performed for the various different ETFs. And so what we want to do is cluster the underlyings based on beta and P&L, and we'll talk a little bit more specifically about what we mean. And I don't know if there's going to be a homework assignment. Probably not. I'll probably, again, similarly, just create a homework assignment that can be optional for those who want to play around with these concepts more. Okay, so, and let me just, well, let's look at the data first, and then I'll talk a little bit more about what I mean by beta. So import pandas as PD, import numpy as NP, import sklearn, import seaborn as SNS, and import matplotlib.pyplot as PLT. Great. Let's go ahead and read in our data. df cluster equals PD. Read CSV. df cluster. Okay, so here's what these mean. So here are the various underlyings that the trading strategy was applied to. Here's the daily average P&L multiplied by some factor like 100 or something like that. But the scale of this doesn't really matter all that much. What matters are the sort of relative differences. The beta that I've calculated here is the beta to the strategy applied to SPY, not SPY itself. So the beta is right, the correlation with the SPY strategy, and then normalized by the ratio of the standard deviations. And the underlying idea is I think there's some of these underlyings that should behave more like SPY and some that should behave less like SPY. And then, of course, it's going to be profitable for some underlyings and not profitable for others. Okay. So let's also bring in some additional information about the underlyings. DF. So what does that look like? So I think I just grab the columns, the column of underlying symbols. And then let's say DF. Oops. PD.read. DF universe. DF universe merge. How? There we go. So this just brought in some additional, what's the name of the ETF, to give you a sense for what is the nature of the underlying. Okay, I'm not going to type this out, but the next thing I want to do is check for some outliers in the data. So if this graph is basically all these individual points are the different underlyings, and here's beta running across here, and here's P&Ls running across here. And these seem a little bit suspicious to me, these kind of outliers. It's always difficult to say. I think when I look through the data, those do have very few points of data around them. So, but they just look kind of a little bit out of whack, and I know this data wasn't the cleanest, so I'm going to go ahead and just remove those underlines. And I isolated them basically by these extreme P&Ls. So let's just query for which underlyings those actually are. P&L less than -8 or P&L greater than 5. And so as we can see, it's GDX, SLV, and UNG that seem like outliers. So let's remove those now. So let's just look at that. Okay, that worked. So DF cluster. And we'll just take a look at the top. Okay, and let's regraph. Okay, there we go. So what I want you guys to do in the next few minutes is take a look at the graph and see if you can just think about how you might partition this into 4 different clusters. And we can talk about why I chose 4 after that. So why don't I give you a few minutes to do that. Okay, hopefully you guys have kind of had a chance to map it out a little bit in your mind. I won't go too much into what I thought, just because I've seen the clustering now. The one thing I will say is that I noticed this seemed to be a pretty kind of distinct group, and I felt like any clustering would probably separate those out. Let's see if I was right. Okay, so now we'll go ahead and give clustering a try. So we'll import the constructor. We'll isolate the features. So we want to now fit our clustering, and I chose to do 4 groups because I was hoping before, in the outset of this, that there would basically form 4 groups. Those with high beta and high P&L, so highly correlated with SPY and highly profitable, highly correlated with SPY and unprofitable, low correlation with SPY and highly profitable, low correlation with SPY and unprofitable. So let's see if that kind of bears out. We can now go ahead and fit our clustering. 100. I think n in it determines the number of times. Oh yeah, n in it, right, is the number of different times it's going to be run. You know how I mentioned that k-means clustering gives you a local solution and you want to do it multiple times. Well, n in it is the number of times it's going to run. So I said 100. And then I'm going to set my random state to 0 just so we always get the same result. There, now it is fit. So k-means labels is what holds our labels. So let's add a column that holds those, df cluster. And I want to change these to strings actually, because that's going to be useful in the visualization that I do. So that's all this does. Great. Okay, so now we have our groups added. And let's just take a look at the clustering here. And I kind of noticed an issue with this clustering, which is why this was called the first try, and we're going to do a second try. I want you guys to just take a look and ponder a little bit and what your observation about the clustering is. Okay, so the thing that I noticed when I looked at this is that, well, first of all, I was surprised that these things didn't get clustered together. And then I realized that basically everything with similar P&Ls was getting clustered together. And that is because the order of magnitude of these P&Ls is higher than the order of magnitude of the betas. So lesson learned, you have to scale your features. So let's scale and then reperform the analysis. From sklearn, pre-processing, import scale. Then we'll scale our x's. When clusters equals 4. Now we've refit. So one thing I'd like you to do is take a look at df cluster, see if there's any observations that you can make about the clustering, about what underlines get clustered together, and if that sort of makes sense to you. And then think about that for a little bit. And then also you have a code challenge, which is to redo the clustering for 3 groups. Okay, hopefully you guys have had a chance to work on that a little bit. You just go over to the answers here and see what observations that I made. So yeah, I thought group 0 was basically high beta, zero-ish P&L. Group 1 was, oh yeah, okay, so these, the actual groupings that come up can be somewhat random. Like the groupings themselves are fine, but the numbers of the groups can be random based on iterations. So it's a little bit strange. Yeah, I don't know, because we're setting the random state to 0. But anyway, so group 1 is, oh no, yeah, group 1 is low beta, zero-ish P&Ls. No, I think this is right. I'm sorry. Group 2 is the extremely low performers, right? These 2 down here that just did really horribly. And then group 3 is high beta, high performers. So a couple things is group 3 consists of QQQ, SPY, IWM, USO, EWZ, and FXI. I believe this is something Brazilian related. I think this is China related. But the important thing is that there are 3 major indices in here, which is something that I anticipated. I knew this strategy was profitable for SPY, so it's not surprising that it's also profitable for IWM and QQQ, and that they would be highly correlated with one another. Another thing that I found interesting was that group 0 contains 7 of the 11 Spider Select funds. So these, and the Spider Select funds are funds that track different sectors of the S&P 500. And so I thought that was interesting that they all performed kind of similarly and had similar correlations to SPY. And that actually is consistent with other aspects of what I know about the strategy. And that another thing that I found interesting was that group 0 also contains several of these emerging market funds, which is just something that I noticed. I don't really have an opinion on that. Okay. And then let's take a look at what 3 group clustering looks like. Okay. Looks like basically these 2 just got lumped in with the low performers, I think. And then this one got lumped in with the high performers. Other than that, it looks pretty darn similar. Okay, then let's move on to the final tutorial for today. So this is a continuation of the data that we were using before, and with the same volatility strategy and on the different underlyings. and we're going to do some visualization of the principal components. So import pandas as PD. So this is the same PNL. Oh no, this is slightly different. It comes from the same place, but let me just read it in and we'll take a look at it. So these are actually the weekly PNL numbers for a variety of the underlyings. I don't think I included all of them because there was not a lot of data for some of them. But for each of the underlyings, these are the weekly P&Ls for these weeks. Oh, I'm sorry. These are not weekly P&Ls. These are daily P&Ls for these days. My apologies. So let's go ahead and fit a PCA to this data. And first we're gonna pre-process it with scaling. sklearn, pre-processing, import scale. So there's our scaled data. And then we'll go ahead and fit our principal components from sklearn. Okay, so there we go. So here's a little code challenge for you. What is the percent of variance explained of the first principal component? And we did 5 principal components. Okay, so let's try this. PCA. What is it? Explained variance ratio is what gives us that. And so as we can see, the first principal component accounts for about 40% of the total variance. So the next thing we want to do is visualize the loading vectors. So if we look at the loading vectors, they are, since there's so many of them, they're kind of hard to look at. Let's just take a look at this. So there we go. So when you remember, we did the level, slope, and curvature of the variance term structure. That was actually, because there were only 4 features that we were looking at. It was pretty easy to just print them out and visualize them, and not visualize them, print them out and kind of see what was going on. Here, there are a lot more features. There's 35 features. So we're going to actually need to do some visualization to just even look at the components. So let's do that. So this isn't very interesting. I don't feel like typing all that out. This is just sticking the components into a data frame. So it'll be easier to use Seaborn. And I also want to grab the clustering results that we did before to see if we can see any interesting patterns with the principal components, the loading vectors, and the our k-means clustering. Okay, so now we've got our groups in here as well. So let's merge those together. df components. So here are the loading vectors going along here. And let's go ahead and visualize the first component. Okay, so your discussion question is to give an interpretation of the first principal component. And then your coding challenge is to look at the other principal components and see if you see any interesting patterns. All right, so this first principal component is clearly just saying that all the strategy seems to make money for all the underlyings most often. So most days, if one has positive P&L, all of them do. They tend to all rise and fall together. So as far as the other principal components, let's see here. So this is interesting. I don't know what I see here. I mean, this group seems to rise together, but they are all going in one direction. These are all kind of negative. So maybe there's kind of like negative correlation between these two, but I don't know. I don't really see a ton there. Let's see. Yeah, and again, it's just hard to, I don't really see a ton. Nothing obvious. Kind of hard to interpret for me. Okay. Now let's go ahead and actually do scatter plots of the scores and see what we get. So the transform attributes, this transform function is what gives you the scores. I don't know why it's called transform, because it transforms the features maybe. I'm not sure. And then let's just take a look at this here. So in the way to interpret this again is, this is the scores of the first principal component versus the scores of the second principal component on the y-axis. Excuse me. And I really don't see a ton in these. Just, I wish I had applied the color. I couldn't figure out how to apply the colors in here too. Tried messing around with it a little bit, but didn't quite get there. One thing you can see pretty obviously is that there's a lot more variation in this distribution than these distributions. One thing they do that's a little bit confusing is they change the scales of all of these, which I don't think they should do. I think it would be, it's a little bit deceiving, but so that's what the scores plotted together looks like on some of this data. All right, guys, that's all I had for today.